Next to me is Dr. Detlef Nauck, and he is a Chief Research Scientist for Data Science with BT's Research and Innovation Division. He has already 30 years of experience in data analytics, machine learning and AI. Detlef is a computer scientist by training. He is a visiting professor at Bournemouth University, has published 3 books, over 120 papers, holds 10 patents and has 30 active patent applications. And he will be talking to you about test driving machine learning. Ladies and gentlemen, Dr. Detlef Nauck.
Thank you, JJ. Hi, everyone. I work for BT. BT is the UK's incumbent telecommunications provider, in case you don't know. And we have a research department out in Suffolk, in a small town called Ipswich, where we have about 200 people working in different areas that is important to the company. So things like network security and AI, machine learning, are part of what we do. We're also filing the most AI patents in the UK. So we are kind of very active in this space. And we publish and we go to conferences. And today, what I want to talk about, I've called test-driven machine learning and model factories. So this is about using AI machine learning in practice. So it's not about inventing the next new algorithm and or making deep learning better and faster. It is about how do you use these kind of things that are developed in academia and published at conferences. How do you make sure that when you use it in practice, that you use it in the right way and in a way that it delivers value to a business? And that's not as easy as you might think. Before I go into the topic deeper, let me talk a little bit about the space ethics in AI, machine learning, and data science. You probably are well aware of the discussion that is going on in the media. You have heard names like Cambridge Analytica, and you know the data collection that happens on the internet when you use services like Google, Facebook, and so on. And there's a lot of discussion at the moment, how do you do this ethically? So how do you make sure that you not abuse data and when you make automated decisions that you do this in the right way? And I just want to mention a couple of examples here. GDPR, you may have heard about, that's the General Data Protection Regulation in Europe. And that means, for example, when you make an automated decision about a person that is somehow important, it has to be a relevant decision, not just sending a letter to advertise a product, but let's say you decline a loan or you make something, a decision that is really important, then you have to explain it. Right? If you do this in an automated way, if you have an AI instance and you just put some data in and the computer says no, that's not good enough. You may have to say, why does the computer say no in this instance for this individual? Which means that some models, some machine learning algorithms like black box models, deep learning, you cannot use because you can't explain what they do. The other big topic is bias, which is like an unfair over or under representation of groups or subgroups in your data. So think of facial image recognition, which is very much discussed in the media at the moment. It is known that facial image recognition is biased. Right? Facial image recognition software is biased against dark faces. So if you have a darker face or if you're even male-female bias is there, these systems don't work equally well across all groups in the population. And that's, of course, a problem. And that needs to be addressed. So when you build these systems that are inside these systems, you have to think about how do you make sure that these kind of problems don't come to haunt you later. And this is not only that you, as a machine learning practitioner, that when you build them yourself, that you have to take care of these things. As a company who might want to sell products in that space, you might buy in these kind of solutions. And then how do you know that they have been built to a certain standard and a certain level of quality? The Next problem I want to mention is, how do you figure out that software is doing what it's supposed to do? Right, so if you write machine learning code, you write software. And if you happen to work in software engineering, then you know that you reuse code of other people. Right? You use libraries that somebody has published, and you assemble functions from other code. And there have been a lot of examples in the past where functions that everybody uses have to do with security and encryption and so on, had bugs, and which then means that the overall system is insecure. And some software developers complain that people don't write basic functions anymore because everything that they can take from somewhere they just take uncritically without checking. But if you're having the problem of convincing somebody that the software that you have built is doing what it's supposed to do, you face a bit of a problem. Because let's say an auditor comes, right? So if you run any kind of system in a company or in any kind of public space, you may have to prove that this thing isn't going to explode or harm anybody. Right? And this is what regulation and auditing does. So they come and check, have you built this thing to a certain level of quality, to a certain standard. And so then you have to basically say, okay, this is what I did. And you can check here, if you wiggle here and rattle there and check this screw, then you know it's going to be safe. And this works well with kind of physical systems. You can take them apart and put them back together and check them. But with software, you can't audit software. There's no software auditing process. So you won't be able to prove to somebody that the complex system that you have built, like that is the autopilot for a plane, or that's an AI system that decides about loan applications, does actually what it's doing, what it's supposed to be doing. And the header here is called Franken algorithms. So you assemble your algorithms by using other algorithms. And so how can you make sure that what you built is of a certain quality, based that you might not know what the quality of the other things is that you assemble. And this is a kind of well-understood process when you build cars or machines, planes. There's quality assurance, and every piece that goes into a car or into a plane has gone through this process. Every screw that you put into a car or into a plane has gone through a quality assurance process, and you know that it won't break under certain conditions. But you can't prove this for software. So if we come back to this space of machine learning or data analytics, what are the kind of challenges that we face when we want to do this in practice? So obviously, machine learning learns from data, so you're using data. When you do this in academic setting, you typically have clean data that somebody has assembled for you, or has checked, or you have assembled it yourself so you know what's in there. In a practical setting, you very often have no clue where the data comes from, if the data has been messed with, if there's if somebody has an interest to fake the data, right? So if you get data about people, how they work, how they run processes, they may have an incentive to lie because you use the data at the same time to manage their performance. That becomes a problem. So you have to think about data provenance, where does it come from, data quality, is it error-free, and is there bias in your data? So this is the first stage where you can be caught out by bias. So facial image recognition systems, they have been developed by young, white, male computer science students, so obviously they have a bias towards these type of faces. Then you can have model bias. So not only bias from the data creeps into your model, when you build your model, your own bias, your own unconscious bias that you have goes into the model. So you have to catch that. Model comprehension, I mentioned this. So if you have to explain the output that the machine produces, how do you do this? Can you do this? And then the ethical domain that I already mentioned. So these are the kind of things we want to think about when we use machine learning in practice. This is mostly relevant for non-academics, so people in industry often think, oh, I just buy myself out of the problem. So I go and buy a fancy tool that does all of these things for me. And you find in machine learning and data science, this kind of approach, yeah, you get a massive environment that does all of these things for you. It automates the machine learning process, it manages your data, it deploys your solution, it monitors it in live. And if you look at what you can get to do these things, like Amazon, Google, Microsoft, the environments in the cloud that they offer, they go for this kind of comprehensive attitude. So just come into my environment and I give all of these things for you. But it also means that you're tied in to one vendor and you have to do the things they want you to do it, and it might not really work for you. And very often when you go out into companies, you find they have IT equipment from 50 years ago. They have different silos all over the place. The data is copied all over the place. You don't know where's the ground truth. So it is very, very difficult to say we just have one coherent solution that we push into an environment or into a business to do this kind of stuff. So as an example, if you want to go from A to B somewhere on the planet, you have to cross a number of roads. So if all your roads look like this, then you're not buying a car like this, right? So you need to think of the kind of tools you want to use for your solution. Are they adequate for the job? And these kind of comprehensive machine learning environments are more like the sports car approach. They're very convenient, very flashy, they look nice, but they typically don't work when you have to drive on dirt roads, which means you have to apply them to 50-year-old IT environments. So this idea of a model factory is more like a tool bench approach, right? And if you work in academia, you probably have this kind of mindset anyway. You take what gets the job done, right? You focus on solving a particular research problem, and you're not so much fussed about that you get a streamlined implementation and integration into processes and things like this. So this is not an unusual way of thinking. The idea here is you have a workshop approach. You combine the tools that get the job done. So instead of thinking when you're in an industrial setting, instead of buying a fancy car, think of the highway code that tells you if you have to go from A to B, these are the kind of rules you have to follow, right? So here you may not be able to overtake, and here you can't turn left. So you have all sorts of restrictions when you want to push a solution into a business environment. And you have to follow certain quality standards. That means if you build a model, you have to tick a few boxes in order to make sure it's doing what it's supposed to be doing. And so think of this as a set of rules, as a set of guidelines that you want to follow. And that's what you do when you assemble things. And so you step back from this thought, I just chuck my data into a tool and out pops an AI solution that I can use. And when you think about the process of building something that makes automated decisions, and thinking that you do this in software, then you can already think of a few tools that you might want. So software development requires versioning. You get things like Git. You need to test. Software development needs testing. You need orchestration, right? So you have different things that need to come together, and that needs to be orchestrated. So how does my data move into the learning process? How does the model that I generate move into a production process? How do I get it out again and replace it with something else? These kind of things. You need to document everything you do. The one important aspect of this space is reproducibility, right? So if you build a model, then you have to be able to build it again. Excuse me. You have to be able to build it again. So especially in industrial environments, obviously, it's not one person doing all of it, right? So one person builds a model, changes role, somebody else has to take over. They need to be able to build the same model again with new data. So that means thorough documentation of everything. and a governance process that makes sure that people follow process, that it's not a cottage industry where you have little geniuses building machine learning solutions, which then nobody else can do once this genius has left the company. If you think around what could you automate in this process, because obviously once you want to push something into production, you want to automate as much as possible. Data pipelines is relatively easy to put in place. So does my data flow from where it's created to where I want to use it? Model build and test can be automated. Right? So the people who say I want to go into data science and have this idea that they craft great models that are win the Kaggle contests, that's not the reality in industry. So model build is more like an 80-20 approach. You try something simple. If it's good enough, that's what you're going to use. You're not wasting time on tuning the last 10% of performance out of it. Deployment is easy to do, has been done in software engineering for decades. In-life monitoring is important. Once you have deployed a machine learning solution, obviously what you do is you make automated decisions. That's what it's for, right? That can be very trivial. It's a marketing context, so you send out emails, letters, SMS to customers to convince them to buy stuff, or you place ads in web pages and check if people click on them or not. But you need to check if your model actually delivers the value that you think it should deliver. So you do A/B testing, right? So you have control groups. So apply your model and you don't apply your model and you check what's the difference, and the difference is your model, so hopefully you get a positive difference, then you know your model produces some value. You can automate this, and you should, so it's getting done. And reporting you can automate to some extent. The difficult bits, and this is where the people skills are required, so where the jobs of the future are to be had. Data wrangling, right? Putting data into the right shape for it to be analyzed, understanding it. This is where you need domain understanding, and this is where companies needs to invest to get their data into order and sort out their data silos and understand really what it is they have and treat it as something valuable, not just as something that comes out of the exhaust of processes. And data quality monitoring is difficult to do. It's what you do as a data scientist when you start to explore your data, right? You understand really what's in there. And what comes out of it is you can write down quality rules. This is what the data should be like. And you can't really automate this easily. And the hard bit is the feature crafting. So now you have your data, so which of these data columns you have, how do you combine them in a reasonable way that you get something that a machine learning algorithm can pick up and make sense of? So this is where data science and domain knowledge combine, and this is the hard bit. So this idea of test-driven analytics, using testing to make sure that machine learning processes deliver, this idea comes from software development, right? So when you professionally develop software, what you do is you first write test cases. I want my software to produce this output if I give this input. And you write these kind of test cases, and there are environments that help you do this. So that means every time you compile your program, these test cases get executed automatically. If one fails, the build fails, and you get information about what has failed, and you can go and fix it. And only if all your test cases pass, then the build is complete, and then it can go further down the road into production. For machine learning or AI environment, it becomes much more complex because you're not only building software, you're also working with data, which can be right or wrong. You're producing an artifact, which is a model, which might be right or wrong. And you're making decisions based on this model, automated decisions. Right? And what does automation allow us to do? Make more mistakes faster. So you have to build mitigation into your automation. So here's a kind of a flow chart of the kind of stages you go through when you do machine learning and deploy it. So you start with a data repository. That's the kind of the first place where you want to do testing, right? So ideally, you prevent wrong data going into your data repositories. And if you work in databases, you may know triggers. Triggers is something that every database has. You can basically say when you have a database schema or table, the data that I put into this table has to tick certain boxes, has to meet certain conditions, otherwise you can't store it. This is an idea that comes back from the 1980s when databases were mainly used for transactions, right? Booking hotel rooms and stuff like this. You want to make sure that you don't sell a hotel room twice and these kind of things, so these kind of checks were built in. Nowadays, databases are more used to dump data that comes out of processes. It's not so much transactional anymore, and so these kind of checks, nobody does them anymore. Right? So you can easily produce wrong data that comes out of a process, and then that can have bad repercussions later if you don't check what's in your data repository. Because fixing it afterwards is either impossible or very costly. All right, then you go into data wrangling. That means you pick your data out of your repository and you try to make sense of it, put it into a shape that you can work with. And at this stage, you can test. So first of all, what you do is you write software, right? So you write queries against your data repository. That's already software. So you should test it, you should version it, keep it, so that somebody else can pick it up and reuse it. So this is where you should start applying software development technology. Then after that, you have understood what your data is like. So you can say things about it. You can say this column should be numeric, the numbers should be larger than 0. Here the average should be between 1 and 2, whatever. So you understand your data, you figure out conditions, you can make assertions about the data, and you can write them down as tests, because that comes in handy later when the data goes through your model, because it should be exactly the same data that you've used to craft your model will later go through your model to make decisions. So you can reapply all of these tests if you have written them down and make sure that the data that you base your decisions on is of good quality. In feature generation, again, you make decisions about the data, how to combine it, how to take 2 columns and craft a 3rd column that tells you something that is more important or more relevant for modeling. Just very simple example, if you want to do fraud detection on credit card transactions, what is a very valuable piece of information if the billing address is different from the shipment address, right? Shipping address. So a fraudster would never ship to the address of the cardholder. They would ship whatever they order to another address. So a very useful feature is to compare these two, and if they are different, then you flag it. So you have a flag that is 1 if the addresses are different, and you have crafted a feature. Again, this is done by writing queries, writing software, and you want to say something about this feature. If you have a flag, it should be 1 or 0. If there's a 2 or a -1 in there, that clearly shouldn't happen. So all of these things you can write down as tests and make sure that your data ticks these boxes. So then finally you go into model building and you build a machine learning model. And so I probably don't tell you anything new if I tell you that you have to do things like cross-validation when you build models. So you have to understand how well does your model perform on unseen data. So there are some procedures you can follow, for example, cross-validation. And again, it's software, so you build several models, you should version these things, so you know through which stages you have been through until you found your final model. So then you go into deployment. So ideally, the deployment means you pull your latest model from the versioning repository. So it's not that the machine learning specialist, the data scientists, crafts something in R or Python or whatever language they like to use, and then hands this over and it's copied into an environment to work. You want to decouple this, right? Data scientists are not software engineers. So you want to have an infrastructure where you can just pull the latest model from a repository so that your model is always up to date. So if you found a bug and you fix it, then your data scientists can concentrate on improving the model, and when it has passed all the tests, it goes into the repository and your production environment can just pick it up. again, there's some testing to be done here. So if you want to deploy a model, you want to make sure that it can handle the amount of data that goes through. Right? So if you have to decide on a few thousand loan applications per hour, can your model do this? Or does it think 10 minutes for each application before it spits out a response? That means you have to scale up your compute environment. This is not something that the data scientists typically think about. They are looking at the model performance and then they're happy with it. So then you go into application, so you produce predictions. Your models spit out automated decisions. And so you want to make sure that they are as expected. So again, a simple example, let's say you have a fraud detection model and you know that in your base you have maybe 1% of fraudulent transactions. Right? So you want your predictive model to predict roughly 1% of fraud in the transactions. If it suddenly predicts 10%, 20%, or 0%, you know something is off, and you should catch that. And so you want to run in-life tests on the outputs of the model. Then you see the arrow from the features back into the model. So now obviously you're in production. The data that goes through the model should adhere to the same kind of tests that you have figured out when you generated your features. So if you have a feature like the flag that tells you the shipping address is not equal to the billing address, so you would say, okay, this flag should be 0 or 1 and nothing else. And you can rerun this test. So if you have a data record going through where one of these tests fail, you shouldn't make a decision with this particular case. It has to go into an exception queue and somebody has to look at it. That's very important. We had models in production where the data suddenly changed because somebody decided that a certain feature doesn't need to be recorded anymore, or a process has failed that puts data into a database. So the data column just changed from present to missing, and the model happily chucked out decisions. And then people were wondering why the decisions have changed. And this is because these tests weren't built in. And then obviously the decision making, if you expect a certain benefit out of this model, you want to check that the decisions are actually doing this. You have done it in your test. Now you're expecting whatever 10% cost saving or something like this out of your model. So you want to check in life that this is actually happening. And another area where you can apply testing. Okay, let me skip these things. I like this quote. When you build models, just remember they're wrong. Right? So a model is just an imperfect copy of reality, which means you should be aware that you're making a certain level of mistakes. And that also means, in the context of automated decision making, you should build mitigation into whatever you deploy. So if your model makes a wrong decision, then what do you do? How do you catch it? How do you mitigate? How do you solve the problem that you might have treated somebody unfairly in this kind of scenario when you apply your decisions to people? So before we finish, a little quiz. What do you think is the most misused term in machine learning, data science, AI? Any ideas? Any suggestions? Just
AR. Any other suggestions? AR?
Learning, yeah, okay, good. The winner gets a cookie. JJ, give him a cookie, please. It's accuracy. Why is accuracy the most misused term? Don't use it when you talk about machine learning. Here's a very simple example. Base rate fallacy. Right? So if you have something that is very rare and you make decisions about it, that means you get a lot of false positives. Here's an example about a medical test. Right? This test has this decision matrix, so you see the true positives, false negatives, true negatives. So you have, and if you calculate this, you can see that when this test says you are ill, you have only a chance of 1 in 11 of actually being ill. And this is because we have this column at the front here, so you have the true positives. It's 1 in 10,000, which is your base rate, and you have 10 in 10,000 are the false positives. The test doesn't make any mistakes if you are actually ill. It will not say healthy, but it makes false positive decisions. And if you have a very small base rate, in this case it's 0.01%, then your model is 99.9% accurate, but it's not really helpful for making your decisions. So you need to understand the whole performance of these models. You need to figure out where do they make their mistakes and what is the size of these mistakes. And that's particularly important if you buy software from vendors, because they always come with the accuracy. Or if you follow the discussion around facial image recognition, when the police says we make only one mistake in 1,000, but this is because they don't look at the false positives. So actually, the false positive rate in facial image recognition is somewhere between 80 and 90%. Right? So 90% of the decisions are wrong when the facial image recognition system thinks this is a suspicious person. All right, let me finish on this slide. Thank you very much.
Thank you, Detlef Nauck.